Okay, now, given a plane ax1, bx2, cx3 is equal d, x1, x2, x3 is x, y, and z from the previous lecture. Now, a, b, and c and d are known parameters, known constant. Obtain the stress tensor, stress vector relationship. First, don't confuse stress vector, you see, stress vector, see here, with a vector. Now, this is a plane, give a plane, this plane is given. So if this plane is given, I can calculate the unit vector n. Why? Because nabla phi is equal, this vector is equal a e1 plus b e2 plus c e3. This is from the last lecture. See, a, b, and c are real numbers, and d also. So then given a plane, I calculate the gradient is the vector, and I divide by its magnitude. So n is a unit normal vector to this plane surface. It's given. Now, you see, don't confuse a stress vector with a vector. F is a vector. T is a stress vector. T is force, for instance, a vector divided by S. You see, this is S. See? Now, what is the unit of T, the stress vector? Okay, is force divided by area. So this is stress vector. Don't confuse with F. Now, you see, for different A, B, C, we have different gradient. If you have a different gradient, you have different normal unit normal to the plane. So that's why we write, in general, F, you just put an index. N is a normal unit vector, n unit normal vector, because if I change A, B, and C, I change the plane. If I change the plane, I will change this the unit normal vector to the plane. That's why you put T n over here. This is stress vector. See, this is stress vector. Is force divided by area. Force, obviously, is the stress vector times the area. You see? Now, recall that. We already did that. You have an area delta S, and capital N is a normal to this delta S, and N is a normal to this projected area. So this projected area, you just make the dot product between these two normal. So there's a normal N dot this normal N over here. And attention, N, the magnitude of N is equal 1, and here the magnitude of N is equal 1. That's why N dot N is a cosine of alpha, because the dot product will be magnitude of small n is 1 times the magnitude of capital N is 1 times the cosine between these angles, between this vector over here and this vector over here. You see, we will apply this as we did before in some lectures that we did just over here. This will be very important. Now, you see, this is capital delta S over here. Now, I will project this area here on the x2, x3 plane, which I do like this. You see, this is this plane over here, you see? I'll project this plane. So the normal to x2, x3 plane is E1. You see, don't forget, the magnitude of E1 is equal 1. Now, the magnitude of n, you see, the magnitude of n is the normal to the plane, okay? This magnitude is 1. So to obtain, given this delta S, to obtain the project area in x2, x3 plane, you just do the dot product. Look how easy. You see? It's the same here. You see? Delta S is equal the dot product of these two unit vector. What is the unit vector of this big delta S here? Is n. What is the unit vector of this project area right there? See? It's E1. So n dot E1 will be cosine of what? You see, that's the angle between E1 and n. You see? That's the cosine. I'll call this angle alpha 1. So the project area on x2, x3 plane, I call delta S1. Because this delta S1 is related to E1. Now we can do the same. If I write delta S2, let's put here, delta S2 is equal, now delta S cosine of alpha 2, that's the blue one here, alpha 2. What is alpha 2? You see, alpha 1 is the angle between n and E1. Alpha 2 is the angle between n and x2. Here, look, this is x2. x2 is right here, you see? So there is an angle between n and E2. So I'll get the project area, attention now, the project area is the area which E2 is perpendicular, so it will be this area over here. See, this is ds2. So ds2 will be delta S, this area over here, projected, okay, in the plane x1, x3. The same now we do with delta S3. This will be delta S cosine of alpha 3. You see the same, okay? What is alpha 3? You see, look, this is E3. Let's put just a bar. This is a vector E3. You see the angle between E3 and n, you see, that I call alpha 3. You see the angle between n and E3 is alpha 3. So the unit vector is E3 and the unit vector is n. The project area will be perpendicular. You see, it'll be this area over here. You see, this area over here is ds3. Is the area in which E3 is perpendicular. It's just delta S3. Why I'm doing this? Because now we will apply Newton's second law on this tetrahedron over here. Consider this body here, and F1 till F6 are an external load. Suppose I cut this body in a certain angle, okay, the plane I cut. I have a section here, this section here, I cut it, it's the same section there. Now, depends on this angle, I have a normal vector here, the unit normal vector. So, if the inclination of this plane change, the normal vector change. Now, let's analyze this section over here. Okay, let's analyze what happened in this section over here. Look, because I cut it, okay, now, before and now, they are in equilibrium, these two parts. If I cut, it appears here, the influence of this right body, the right cut over here, that's what we call the stress vector here. It's called T, influenced by N. Let's put that an arrow here. You see, this stress vector appeared here because I analyzed the cut. You see, look, if I joint, okay, this will be here just with equilibrium with this over here. You see, this is the same, this opposite direction, this T. Let's put a vector here, T of N. You see this equilibrium. So this here appeared influenced by the lefty cut. You see lefty body here. You see the left part. The lefty part, okay, acts on this section over here using this through this stress vector. So the right part influence the internal force over here. This internal force, T is internal and T is internal. So this force appeared influenced by the right part of the body, and this one was influenced from the left part of the body. So F1, F2, F3, and F4, okay, these result in this here. Now F5 and F6 influence the left part of the body of this, and this is equilibrium, so this direction is opposite to this direction. That's what you call a stress vector. Stress vector, which depends on N. You see, if I change the inclination of this cut, you'll be another one here because N will change. Now let's do the same idea using a tetrahedron here. You see, look, the same idea. You see, that's a plane, the plane here. I'll give this plane, okay? If I give this plane, I will give the normal vector, which is gradient phi divided by the magnitude of gradient phi. That's a unit vector. Now, you see here I have on this face over here, you see this is x2, this is x3, this is x1. Now, I will do, you see this is sigma 2, 2, because this is x2, no? From this. Now, here is sigma 3, 3. And there, parallel to x1, you see, is sigma 1, 1. See, parallel to x1. Now, these are called a normal stresses. Now, let's write the shear stress. You see, x3 in this direction, so I have here, now sigma 3. Now, this is parallel in this case, okay? It's quite easy now to understand. This is 2, okay, that's 2. So this is 2. It's parallel to 3. So this is minus. That we'll see later, okay? Now let's do this. It's quite easy now, you see? Now, on this plane there, you just mark the opposite here. This is sigma 2. Now it's parallel to x1. See? So we have here the three components of the stress vector. Attention, this is shear and this is normal stress. We'll do the same on this area over here. see these three stress vectors. So we do like this. This is a parallel, the opposite direction, see? And this is the opposite direction to that, you see? This is parallel to x1, this is parallel to x2. So you'll be sigma 3 parallel to x1, sigma 3, 1. And this one is parallel to x2, so this sigma 3, 2. Okay, on the same, on that surface over there, so here we have from here and from here. Now this is sigma 1, you see, because it's perpendicular to x1, now parallel to x3, sigma 1, 3. And this is sigma 1 parallel to x2, the sigma 1, 2. Now, we will apply the Newton's second law. Newton's second law involves force. These are not forces. See? This is force divided by area. Okay? And this here is, you see, this is T of n. You see, this is T of n, because you see I just cut it. So the influence of the right part is T over n, exactly like I did here. You see, this is a tetrahedron. You see, there is one in contact with this, which I cut at a certain angle, which gave me the unit n. Do you understand this? So this here must be in equilibrium with the sigma over here. See? That's why we're going to have the stress tensor stress vector relationship. See? The sigmas are called the stress tensor, and T is the stress vector. We, using Newton's second law, we want to relate the stress vector with the stress tensor. Let's apply Newton's second law. It's force. See? Look, let's project this stress vector, you see, this stress vector on this x1 axis. So this will be T1, you see, now related to the normal vector n, T1 delta S. So T1, you see, T in this case divide by, this is the force is T times delta S. So this is force, you see. This is important for you to understand. This is force. Force is the stress vector, which is force divided by delta S times delta S. Now, you see, look, all these component, stress tensor component, they are negative because according to the definition, you see all of this area over here, this one, the stress, the components, you just write in the negative direction of x1, x2, and x3. So you see, this is sigma 1, 1. You see, this sigma 1, 1, sigma 1, 1, times this area over here. So what is this area? This area is delta S1, as we did in the last picture. Now, here is sigma, you see, sigma 2, 1. Sigma 2, 1, what is sigma 2, 1? You see, this is 2, x2, this is sigma 2, 1 over here, in the negative, okay, in parallel to x1. So this is minus sigma 2, 1 times this area over here is delta S2. Now the last one is sigma 3, 1. You see, look, this sigma 3, 1, this is parallel to x1 axis. So this is minus sigma 3, 1 delta S3. So this is delta S3. Plus the body force, the component body force on this x1. Attention now. The body force is proportional. See, this is proportional to the mass. The mass is proportional to dV. You do remember dm is rho dV. You see? All these terms over here, they are delta S. So, as delta goes to 0, this goes to 0 faster. That's why this term here, we can bend this term in relation and comparison on this area. The term involves areas. So now let's cancel delta S. Why? Look, delta S1, you see, is delta 1 cosine of alpha 1. Delta S2 is delta S cosine of alpha 2, as you did before. And delta S3 is delta S cosine of alpha 3. So we can cancel all this delta S over here. Then there's a relation between the stress vector, you see the stress vector and the stress tensor. Look, sigma 1 cosine of alpha 1 plus sigma 2 cosine alpha 2, sigma 3 cosine alpha 3. Now you see here, look, 1, 2, and 3. So that we can represent it as a dummy. You see, that's JJ over here, and this is still 1. This is a free index. You see, this is 1, and 1. Now we can, for the x2 axis, from here we can write, look, t, now Tn, you see, 2 is equal, look, sigma j cosine alpha j, this will be 2 here, you see, 2. And for the x3 axis, this will be 3 n is equal sigma j cosine alpha j, now it's 3 over here, this is 3, you see. So we can write in general, you see, t, there's a vector n, I is equal sigma j cosine alpha j, this will be I, you see. Now you see the relationship between the stress, attention, there's a stress vector, this is a stress, in this case the stress tensor, you see this sigma ij, let's put I right here, you see. Now attention, cosine is dimensionless, so sigma ji is force divided by area, the stress vector is force divided by area. Also we can represent this as a matrix. You see the product of this rho matrix, okay, this rho times this matrix over here is this stress vector. This here is the stress tensor. You see, actually, vector is a tensor, okay? When you say stress tensor, it means that it's stress second order tensor. It's better to write, you see, to write exactly. This is stress, it's better to write this. Stress second order tensor. This is stress vector or stress first order. Let's put first order tensor. See? That's a relation between the stress first order tensor and the stress second order tensor. Now, this here is dimensionless. Dimensionless. This here is force by area. Force by area. Obviously, this here will be force by area. So a stress vector is a force by area. Now we can check. You see, look, first row times first column. You see, I'm sorry, here, first row times first column. You'll be this term over here. You see, this is first row, first column. So T1n will be the first row times the first column, which is right here. See, first row cosine alpha 1 sigma 1 1 is here, plus cosine alpha 2 sigma 2 1, cosine alpha 2 sigma 2 1 is over here, plus cosine alpha 3 sigma 3 1, cosine alpha 3 sigma 3 1. Now T2 will be first row, second column. And then T3 will be first row, third column. We represent Ti here. See? Now that's a relation between a stress tensor, a stress second order tensor, a stress first order tensor. It's a vector. This relationship.